Hello, everybody. Oh, my camera's not there. There we go. Welcome back to Computer Science 4303. It's been a minute, hey? We had a little bit of a strike. Fortunately, that seems to be resolved now, and we've been told to get back to work. So welcome back, everybody who is in the class and who was following along with the lectures online. So we can see here that we have sort of a new class schedule, or at least a rescheduled class schedule. We missed a bunch of lectures because of the strike, and so we had to move that around a little bit. If you're out there, just let me know if you can hear the mic. It's been a while since I did this. I'm pretty sure it's fine, though. Or someone would have said something if you can't hear me. So we missed these 5 lectures, and now you can see that today is February 16th, Thursday. We're going to be talking about grid algorithms, but you see here I've sort of put this thing out of order on Tuesday. No, you didn't miss a lecture. What's going to happen here, in order to give you enough time for the assignments in the class, I wanted to release assignment 2 before the midterm break, because the midterm break is still going ahead next week. And so what I'm going to do is I'm going to do this lecture today on grid algorithms. It's going to take about an hour. And then the lecture for assignment 2 is right here. I'm going to use the same lecture from last year's class. So assignment 2 is the same as last year. And so go ahead and watch this lecture video, which is all about assignment 2. So if we look at this here, you go here and the download link for assignment 2 works already. So this is me from almost exactly a year ago explaining the assignment, and your assignment is exactly the same. So today's lecture is approximately 2 lectures. So as soon as this lecture stops, or I guess anytime you want, you can go watch the assignment 2 lecture, but it is available right now for you to do. So there's a lecture for that. Just one note that I have here on the spreadsheet, just note that the video is from winter 2022, not 2023. So any dates that are mentioned or any spreadsheet that's shown in that lecture, just realize that that was last year's lecture. So all of the dates here are the correct dates. Okay, so for example, this assignment 2 on vector fields is being released today, and you'll have until March 9th to do that assignment. So you'll have 3 weeks for that assignment. Then there'll be one more assignment, which has been, again, pushed back because of the strike. It's going to start on March 3rd, and you're going to have until March 28th. So for the next month or so, you're going to have 2 more assignments to do. So hopefully you did a bit of work on the project. While you had some time to do that, I saw that I was added to some GitHub repos, so that's great. So yeah, just make sure that you're budgeting your time appropriately, because you still have plenty of time to do these assignments, because there's only 3 of them total in the course. So other than that, not much has changed. All of the due dates for the project are still the same. Okay, so all of these are still the same. Nothing has changed. You have plenty of time for that. And this schedule, I have a couple of lectures that are to be determined down here. That's all going to be changed eventually once I figure out exactly the entire schedule. But from here on downward to about here, all this is rescheduled, so please just go by what this new schedule says. And that being said, I think we're good to go. Oh, the last thing, I mentioned on Discord that I was going to have a bonus office hour today, but unfortunately, I need to go to the vet, and I can't do that bonus office hour today. So I'll do the normally scheduled office hour once we're back from midterm break. But again, I'll be available on Discord. Oh, and the last announcement is that starting Friday, which is the 17th, I am going to be on vacation, so not available for anything for the duration of midterm break. Okay, so I start tomorrow on Friday on that vacation, and I come back on the 26th. Okay, so I'm going to be gone for 8 or 9 days, and I'm not going to be in the country. I may have access to email, so if there's something life or death, I may be able to answer it, but there's no guarantees. All right, so just keep in mind that I won't be around during midterm break to answer any questions, but I will be back the week after midterm break for help with whatever. Okie doke. Let's get started with the lecture. Today's lecture... Oh, we got... PowerPoint is showing up on the wrong monitor. Let's see if this works. Here we go. Okie doke. So today's lecture is half recap from 3200 and half new stuff for assignment 2. So we're going to be talking about grid algorithms, and then we're going to be talking about vector fields and influence maps. So if you did computer science 3200, it's going to seem like I'm going a little bit quickly through some of these slides, but that's because we have done most of this material in 3200 before, but it is very relevant to this course, so we're going to do it again. Okay, so today we're going to be talking about connected states. So we did that in assignment 2 for 3200, so please don't have any, any flashbacks to that assignment. I know that was a tough assignment. We're going to be talking about a distance map, and we're going to be talking about a vector field. And what all of these different grid algorithms do is they allow us constant time lookup after we've computed something. So pre-computation, as we know, is the ability to spend some additional memory and additional time at the start of a program so that our queries like pathfinding or connectedness or distance end up being faster in the long run. And typically, whenever we make a program, it's the query time that we're most concerned with. We don't mind if it takes a second or two when we start the program as long as our queries are really fast. So the connected state stuff, that's going to allow us constant time lookup to see if a path exists between 2 points on a grid. A distance map is going to be a constant time lookup for ground distance between 2 points on a grid. And a vector field is going to be a constant time lookup for all shortest paths to a single goal on the map. So that's going to be really, really powerful. And this is what assignment 2 is essentially going to be, is computing a vector field and a distance map. So what are connected states? States or cells in a grid, we're going to say that those are connected in a grid if a legal path exists between them, no matter how long it is. And so something I'm calling a connected sector in a grid is going to be the entire set of states that are all connected to each other. And again, this is all recap from 3200. So a good... this is a nice refresher, though, for heading into vector fields. So connectivity is transitive, meaning that if A is connected to B and B is connected to C, then A is also connected to C, okay? And we'll talk about, we don't need to worry about object size in this course, so I'll just skip that part. Actually, let me remove that from the slides. Give me 1 second. All right. So connectedness, if we have an environment that looks like this, we may have these two states. These two states are connected. These three states are connected because I can pathfind from A to C, I can pathfind from A to B, and I can pathfind from B to C. So all of these are connected. These two states are not connected because no path exists between them, because I can't go between two different colors. So we all remember this sort of thing from 3200. And then a connected sector is a set of states in the grid that are all connected to each other. So all of these purple states here, you can see that all these states in the environment, you could pathfind from any of these to any of these. Okay, so how did we compute connectivity in that assignment 2 in 3200? Well, we knew that two states are connected on the grid if any four-directional path exists between them. And so what we did was we used a breadth-first search, BFS, to determine four-directional reachability. And we're going to see throughout this lecture that BFS is really, really powerful, okay? So we can do lots of cool stuff with BFS. So instead of computing separate paths between all pairs of points in that sector, we can compute all of them in just one pass, okay? So we can compute the connectivity in one pass. And the complexity of this algorithm is just the number of states or cells in the grid. And so we will be touching each of those cells once, and so the computational complexity is just equals big O of the number of states. So if we recall from 3200, our general uninformed tree search algorithm, which we have a problem, which is the environment, and we have a strategy. And this strategy is something like BFS, for example, or DFS. And so again, this algorithm is very, very simple. We have an open list, which consists of a node containing the initial state. And then while true, if the open list ever gets empty, we return that we have failed, there is no path. Otherwise, we select a node from the open list to expand, whichever node the strategy says to select, and we'll give an example of that in a second. If the state of the node is the goal, then we know that we have reached a solution path. Otherwise, we take that node and we expand it, we produce its children, and we add its children to the open list. So if we want to turn that into breadth-first search, remember we just use a queue as the open list, right? So breadth-first search uses a queue. When we take something off of the queue, we pop from the front of the queue. Otherwise, we push, my cat is yelling to get outside. Is anyone else still buried under the snow? Because our patio has like 4 feet of snow on it from all the drifts, and our poor cat wants to get outside, but he can't. So if you hear some meowing in the background, that's our cat Freckles trying to get out. Oh, here he comes. He can open doors now. That's great. Just 1 second. Sorry about this. All right, so again, to recap, breadth-first search is just taking that general tree search algorithm and using a queue for the open list, and when you want to get a node, you pop it from the beginning of the open list, and when you want to add, you push it to the end of the open list. So that's just a queue data structure. So to illustrate BFS, again, just to refresh all your memories, over here we have an environment. This environment has states in the environment, so states A, B, C, D, E, and we denote that an action is legal in this graph-based environment by an edge being drawn between them. And the cost of the actions of, say, going from A to B is denoted by the weight on that edge. And so going from A to B costs 6, going from A to D costs 1, etc. All right, so I'm really sorry about this. My cat wants to get in the garage. I have to let him in so he doesn't keep interrupting the lecture. So just give me 1 second here. Poor kitty, can't get outside because of the storm. All right, so the process of BFS, as we all know, is breadth-first search. So we are going to take our starting state, construct a search node out of that starting state, and then search breadth-wise. So we're going to take all the legal actions. So for example, A can go to D, so we search toward D. A can go to B, so we expand toward B. And then we start with the leftmost node from this depth, once we've done all the legal actions from A. Now we say, okay, D can go to A, to B, and to E, and so we search all of these. B can go to A, D, E, and C, etc. So we've all seen this before. Just a quick recap of what this looks like on a graph. On a grid, however, it looks like this, okay? So 4-directional BFS on a grid searches outward and outward and outward like this. So you've all seen this before, but we are going to be doing BFS again today, so I want to make sure that you recall all this stuff and all its properties. So properties of BFS, it is complete, which is great. So it explores the entire tree, and so if a goal can be found, it will be found. However, so BFS will find the shallowest goal node, since it explores all nodes at a given depth before the next node. But something that's really important is that BFS is not necessarily optimal, okay? So in general, BFS does not produce optimal solutions, since the shallowest node is not necessarily optimal. It is optimal if the path cost is non-decreasing function in depth, and BFS is optimal if all action costs are the same. So here we go. Here's an example of BFS not being optimal. In this example that we gave before, BFS is going to find the goal state C by going from A to B to C, right? So it's going to find the minimum depth, meaning the least number of actions. But as we can see, going from A to B to C costs 11, but going A, D, E, C costs 7. And so it's not the optimal path, it's just the fewest amount of actions path, or the shallowest path. The time complexity of b to the d, well, it's got to search b actions per depth times like b times b times b times b, so that's b to the d nodes generated, and the space complexity is b to the same, right? So we have to store the entire tree, unfortunately, with BFS, and so that's so the space is the number of nodes generated as well. BFS performance on grids with a closed list, however, will have a space complexity equal to the size of the grid. So that's actually really, really good. BFS will find optimal paths for 4-directional movement since all costs are equal. And so while in general BFS is not optimal, since all costs in a grid, if we're going in 4 directions, are equal, then it will produce optimal 4-directional paths for us. It may not find optimal paths for octagonal movements since the costs are not equal. So just realize that if you do 8-directional movement with BFS, you may not find the optimal path. So what it's going to do, what we're going to do is we're going to use 4-directional BFS to find our paths, because we know it produces optimal paths, and then we're going to use those paths and refine them somehow to produce a better looking path than just moving up, down, left, and right in our grid. So avoiding repeated states, we talked about this as well in 3200. It's one of the most important ideas in search, and it's especially important in search with reversible actions, meaning if I can go left, right, left, right, left, right, then I can infinitely loop in my search, which is really bad. And so most infinite loops and wasted time can be avoided just by not returning to identical states. And so we're going to remember the nodes that we visited and not visit them again. And so this can lead to exponential savings in the number of nodes generated. And if you remember, we did this by introducing the concept of a closed list. So the closed list stores the states that we've already expanded in our search, and it's often implemented as some sort of hash table or dictionary for efficient lookup. And essentially all it does is if we expand a node, we add it to the closed list, and if a node is in a closed list, we don't need to expand it again. And so if the open list is a fringe of unexpanded nodes, usually implemented as a priority queue, or in the case of BFS, it's just a queue. Then the closed list is the states that the open list that have already been popped out of the open list. Okay? So breadth first search with a closed list, you've all seen this algorithm before. The only change is that we have a closed list, and down here we check to see if things are in the closed list. And if they are, we can just skip them. From BFS to DFS, again, the algorithm is the same. We just use a stack instead of a queue. So again, this is what BFS looks like with a closed list, and you've all seen this to death by now, especially having done 3200. So then, how can we compute connectivity? As the breadth first search expands, we essentially are going to mark every cell that it touches and give it an integer. Okay? So if we look at this BFS, as it goes outwards, it essentially touches or expands all of the nodes whose states that we're connected to, right? So every time a state is marked as red, we can just say, okay, this is connected to everything else, right? So we saw this in assignment 2 of 3200. And when we go out through the BFS, we mark every cell that it touches with some integer, and that integer is going to be its sector number, and we're going to store that in a separate grid. And everything that a single BFS touches must have a path that connects it, and because connectivity is transitive, if the start state of the search is connected to state A and state B, it means that A is also connected to B. And so any two cells in the final connected grid with the same sector number are connected. And I gave this example in 3200 as well, where we have, this is the algorithm that we use to compute connectivity. So we're going to start off with a grid that's the same size as the environment. And what we're going to do is we're going to loop through each cell of the, first thing we're going to do is create a new grid of integers and assign them all the value of 0. Okay? So once we've assigned them the value of 0, a 0 essentially means we have not yet touched that cell in the grid. Okay, so the computation has not been done yet for that cell. So what we're going to do is we're going to start up here in the top left, and we are going to iterate to this from this this cell to 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 this cell, and then once we're done this line, we're going to come down here and then do this line and then do this line. We could also do it column by column instead of row by row. Doesn't really matter as long as we touch all the cells. And when we do that search, when we go through each cell, what we're going to do is we are going to check the cell that we are at, and we're going to say if that cell is a 0, meaning we haven't done a BFS from there yet, then do a BFS outward from that location and give those cells a value of the next integer. So for example, we're going to start here. We're going to say, oh, look, that is a 0. So I'm going to do a BFS from there. So I'm going to give it a value of 1. Then we're going to breadth first search outward from that cell, marking everything that it touches with a 1. And what we've done here is we've marked all the cells that are connected to this cell. And that means that anything with a 1 now is connected to that first cell and connected to each other by the transitive property. So then we've done this cell, so we move to the next cell. So now we check this cell, it's not a 0, so we just mark it, we can skip it because we've already done a BFS to that one. So we skip. Okay, here we go. Here's a 0, so I do a BFS outward from that with the next number, and then I've marked all of these cells with a 2, and all of those 2s are connected to each other. Then I keep going until I get to here, and then this gets a 3, and then BFS outward from there, all of those get a 3, and then down here we do the same thing. And what we're left with is this, what I call a sector map, which maps each state to a sector number, and that sector number says, okay, we are connected to all of the sectors or all the cells that contain the same number as me. So here is the pseudocode for that. We are not going to be implementing that again in this course, but it is there for you if you want. So what is the point of going over all of that again? Well, it is all very connected to this idea of a vector field, and a vector field is going to be what this assignment 2 is completely based on. So vector fields, what are they? So vector field is a term from mathematics, and in mathematics, a vector field is an assignment of a vector to each point in space. Okay, so for example, I'll have an example in a second. So it's used in things like vector calculus, differential equations, physics, magnetism. The study of magnets uses vector fields. Think a magnetic field is a vector field, for example. So in game programming, a vector will be assigned to each cell of a grid. So right here where we were doing connectivity and we had an integer assigned to each cell in the grid, what we're instead going to have now, what the hell? This is not letting my mouse escape. Okay, here we go. My mouse was like caught in the PowerPoint. So instead of having an integer here, at each cell location, we're actually going to have a vector pointing somewhere, and that's going to mean something. So that's what a vector field is, and those vectors are going to be assigned two values, so an x and a y value. All right, so vector fields, a vector will be assigned to each cell of a grid, and this vector is going to denote the desired action or direction of movement from that cell. So vector fields in science are all over the place. You know, I said that magnetism is often visualized with these vector fields. Here is an example. Here are some examples on this website here. So anytime we have a magnetic field, for example, we have a vector field. However, in the real world, in the actual universe, these magnetic fields are real valued and continuous, right? Meaning that there's no grid in the real world, right? If we measure the magnetic field at two places that are like an infinitesimally small amount of difference between them, they will have different values. So we are going with some sort of discrete vector field that kind of looks like this, okay? Where each cell in our grid is going to be given a direction, essentially. So the vector in our vector field denotes the direction of movement. And so what we are going to produce for assignment 2 is something like this. So let's say we have a video game, and in that video game, we have many, many, many different things that all want to get to the same point. So my canonical example of this is like if you're playing an action RPG like Diablo or Path of Exile, you may have the player running around, and you may have hundreds, if not thousands, of NPCs or particle effects that want to go toward the player, right? So how are we going to be able to do that? In 3200, we did the A-star pathfinding algorithm, and that was great. It let us find a path pretty easily. But if we have 10,000 points like this or more, then we're not going to do 10,000 A-star searches from each point to its destination. So this is an example of how we can efficiently do multi-agent single goal pathfinding. So no matter how many agents we have, and no matter where they are in the environment, we're going to be computing a vector field, and that vector field is going to tell each agent, if you are here, go this way. If you are here, go this way. If you're here, go this way. And then if each agent follows the vector field toward the destination, then they'll be given the shortest path, or following the shortest path to that destination. And so we can do one instance of a pathfinding algorithm and get paths no matter how many entities we have in the environment. So what we are going to start with is this idea of a distance map. And so I mentioned distance map in the opening slides. What a distance map is, let's say our goal is right here, this red square. A distance map is another grid, the same size as our environment, that is the intermediate step between having nothing done so far and a vector field. So the vector field is going to require this distance map as an intermediate step. Essentially, what a distance map is we have a new grid that is marked with the distance from the goal location. So here, for example, we can see that this is 1 from the goal location. This is 1 from the goal location. This is 2 from the goal location. And this is measured in 4-directional movement. And so essentially, what we do is we start at the goal location instead of starting at the start. Okay, we start at the goal location, the destination where everything wants to go, and we do a breadth first search out from that goal location. And as we do that breadth first search out from the goal location, we simply mark these cells with the depth that they were reached by the breadth first search. And so you can see here that this is just the depth of the breadth first search, but it also denotes the path length of the breadth first search. And what we do in the next step in order to form the vector field is once we have the distance map, how do we get to our goal location? Well, let's say we are over here in this cell, okay? If we're over here in this cell, how do we know from the distance map how to get to the goal? Well, if we are at this cell marked 8, if we went up, we would now be 9 away from the goal. So we're actually getting further away from the goal. So we don't want to go up. Left, we'd be 9 away as well. Right, we'd be 9 away as well. But if we go down, we are now 7 away from the goal. So what you do is once you've computed the distance map, you iterate, you form a new grid, right, where you're going to mark your vectors. And for each value in the distance map, you look at the 4 neighbors and you just draw a vector toward the lowest valued neighbor. And that guarantees that your movement is going to be going toward the goal. Now, in this example, they are using diagonal arrows. In our example, we're going to be using, for example, right here, over at this, or let me mark, okay, right here, this 8 over here. If you go to the right, you have 7, and if you go down, you have 7. So there are 2 ways you can go in order to go toward the goal. You could go right or you could go down. Now, in this example, what they do is they actually choose to go diagonal, down right, and we're not going to do that in our assignment. What we're going to do instead is have a vector pointing right and a vector pointing down. Okay, so you can go either right or down, but we're not going to be doing diagonal actions in our assignment. That's just a slight difference from this diagram. So what we get in the end is exactly this. We get a vector field that allows us to do this pathfinding. And so what's going on behind the scenes in this demo is that whenever you click the mouse somewhere, it sets the goal location. It does a distance map computation, so a breadth first search out from that location, which is almost exactly the same as the connected sector computation. But the only difference is you are assigning a value to all of the cells that you touch with the BFS equal to the depth of the breadth first search. And then based on that distance map, you do one more pass where you say, okay, for each cell in the grid, I'm going to point toward the lowest neighbor. And that's all you need to do to get this really cool pathfinding system done. And then you add some particles and you just go in the direction of the particles. And it's really, really easy. So vector fields for games, sometimes they're called flow fields. Influence maps can be done with vector fields as well. Sometimes they're called vector maps. And they are a very efficient structure for pathfinding in the case where we want many paths to a single goal. So any case where multiple NPCs need to go to a single location, consider using vector fields. And so they can be used to accomplish a number of tasks, not just pathfinding, but we're going to focus on pathfinding for this assignment. So I'm going to go over this. I know I've explained this already, but I just have some slides on this. So the distance map, before we compute the vector field, we need to compute a distance map, which is another grid. Each grid of the distance map, each cell of the distance map grid will store the 4-directional shortest path distance to a single goal cell. And in practice, we will need one distance map per pathfinding destination. And we can cache the maps if it's efficient to do so. Okay? So what that means is that if we have a goal location here in the map, so if the player is here, then we compute a vector field. But if the player moves, we do need to recompute the vector field. Okay? But it's a really quick computation, so it's okay to recompute the vector field. So this is the algorithm, now spelled out a little bit in more detail for computing the distance map. So what we do is we start with a goal location in the environment, and we assign that cell a value of 0. Then we breadth first search all of the children of that cell. So here we have added all of these states to the open list, right? Or all of these nodes to the open list. And our grid, which is our distance map, we give it a value of 1. Oh, just 1 second. So this is the first depth of the search. Coming from 0, we go to 1. Then we breadth first search out from all of those 1s, and we go to 2, right? We breadth first search out from those 2s, we go to 3. And then what we have in the end is a distance map. So anywhere in the environment that I want to pathfind to this goal from this start, I know that I'm 15 away from this goal. So what I can do here is I can say, okay, how do I get to the goal from here? Without even knowing where the goal is, I can just say, oh, look at this. Going to the right or going down. Those are where my distance decreases the most. And so I can either go right or I can go down in order to reach the goal the fastest. So this distance map is computed via a BFS in a similar way to the connected sectors, but instead of marking each cell with the same value, we give it a value of the parent plus 1. And so the distance map cell's initial value is -1, and then any distance map cell that has a value of -1 at the end of the computation is not reachable from the goal. And the reason we use -1 is just to show that, okay, if it's -1 distance, we can't go there because 0 is the distance from the goal to the goal. All right, so now how do we do the vector field computation? Well, you could probably figure this out on your own, but just for completeness, from a distance map, it is very easy to construct a vector field for pathfinding. Each cell gets assigned a vector pointing to its lowest neighbors. That's it. And optionally, if a cell points to both left and up, we could replace it with a diagonal left up. But we're not going to do this in our assignment. We're just going to do multiple vectors. So here we go. We have we're going to start off step 1, distance map. We're going to compute the distance map out from a goal. Step 2, point to the lowest. That's it. It's just 2 steps. You have an environment, BFS outward, compute the distance map. Step 2, use the distance map, point to the lowest neighbor of the distance map. And then we get our vector field, which is pretty neat. So these vector fields, the last 4 slides came from this tutorial. And so if you want to know more about vector fields, you can go read this if you want to, but it's a really simple computation and you should all be able to do that. So some of the performance notes for BFS here, implementing BFS iteratively with a queue, if you recall from 3200, it actually results in pretty poor performance. So I'm going to go over an optimization here for you that you should do in this assignment in order to get really fast vector field computation. Vector implemented queues. So if we use a queue in C++ or in JavaScript or whatever, if we remove from the first element of a queue, then it has to shift all of the elements to the front, okay? Which in practice can be very, very slow. What do I mean by this? Well, let's draw a vector down here. This is my rudimentary vector. Here we go. So we've got a vector, it's got 6 elements in it. And as part of a queue, we may have some values here, right? 6, 7, 8, 0, 1, 2, whatever. So we have a queue, we have some values in there. Now, as part of our algorithm, we want to pop from the queue. Popping from a queue takes the first element and then deletes it. All right? But in practice, this is about the slowest operation that you could do. Okay? Because in an actual vector, if you're using a contiguous vector, what has to happen in order for this to be implemented is everything in the vector now needs to be shifted to the left to fill up that first spot in the queue, right? Because this is index 0 of the queue, this is index 1. If you remove this index, well, now this one has to be index 0, right? And there's no magic way to do that other than to shift everything to the left. And that's a very slow linear time operation. So let me just get rid of those annotations. And so also, another optimization that we did in assignment 2 is that performing lookup in a closed list can also be slow if it's implemented very poorly. So I'm going to show you some optimizations to avoid this really expensive queue operation in this assignment. So what we're going to do is we are going to simulate the behavior that we want in a queue, but we are going to be using a vector. Okay, so it's just a vector, but we're going to eliminate the need for those deletions and those expensive shifts, and I'll show you how to do that. So to insert into the queue insert goes to the end, right? So we can use a vector for that because vectors push to the end anyway. So to insert into the queue, we push the state into the back of the vector as we normally do. But instead of removing, like actually deleting from the front of the queue, we're going to leave the value there and just advance a pointer. Okay? So instead of checking if the queue is empty then, we're going to check to see if the pointer is pointing to the end. And here's an illustrated example of this to show you how well this can work. All right. So here's what I mean by simulating a queue with just normal operations on a vector and the advancement of pointers. So let's say I'm here. I've got my open list queue. So I've got one element in my queue, right? It's just a vector of size 1. I've added the root node, for example. Now, when I expand that node, maybe I have 3 children, right? So I add those 3 children to the queue. This cell here, that is what I wanted to now delete from the queue, right? So that this one would be the front of the queue. But instead of actually deleting it from the vector, I'm just going to keep an index. And this index points to the front of the queue. So I'm going to actually just leave this value here. So I'm going to waste a little bit of memory, but speed up my implementation dramatically. So I'll keep an index to now say, hey, this is actually the front of the queue, right? So when I pop from the queue again and add some things, oh, this is the end of the queue, by the way. What I'm going to do is add some more children to the queue. And now I advance this, the pointer to the next element. So I've already expanded those things. I've removed them from the open list, but I actually leave them there. And now this is the pointer to the front of the queue. Maybe now I don't have any more children, but I'm advancing the pointer toward the end of the queue, right? I'm continuously popping and popping things off of this queue. And I know that I've reached the end when I've popped everything from the queue. And the way that I know if the queue is empty is if the starting pointer is equal to the ending pointer. Okay, so these don't have to be actual C++ pointers. These can just be indices. And what we're doing here is we are never actually freeing up this memory, but we are trading that memory for speed. All right. So we know that this takes a little bit more memory because we're not actually deleting things from the vector, but it's so much faster. It is like orders of magnitude faster to do it this way than actually removing things from the vector. So when you go to do your queue for your BFS, you can do this. It's fine. And also another little optimization is when we did BFS using the standard tree search algorithm, we created a node data structure, right? But we actually don't necessarily need to make a node data structure and put that on the heap and put that in here. You can actually store states in here. Now, that's just like a little teaser for an optimization for this, but do it however you get it to work. Do that for the assignment, and then look into making it a little bit faster because the solution code, I want you to try and get as fast as the solution code. The solution code is really, really fast for this assignment. Another optimization that we can do is on the closed list. So the cool thing, this is really, really cool, that you can do away with the closed list. You do not need a separate closed list for this assignment. Why? Because we can use the distance map's initial values as a constant time closed list query in lieu of a set, right? So watch this. Initially, we're going to assign the distance map cells a value like -1, for example. So the distance map is going to be all -1s. Any state which has not yet been visited, so as we do the BFS, we're setting the values 1, 2, 3, 4 out with the BFS. But any state that has not yet been visited is still going to have that value of -1. And so in order to check if a state has been visited by BFS, just check to see if the distance map is not -1. Right? So isn't that cool how the distance map is also acting as a closed list for the search. And so we do not need a distance map, a separate closed list structure. We can just use the distance map. If you can't figure out how to do this, just use a separate Boolean grid if you want to as a closed list. So what does that look like? Right? So here, if we've BFS'd outward from here, you can see a bunch of these things have a -1 value, right? So if I'm saying, okay, I'm at this node right here, this 3 on top, I'm looking at the children, are they in the closed list or not, right? So I look up, it's -1, so it is not in the closed list. This is -1, not in the closed list. This is -1, not in the closed list. This one is not -1. So it is in the closed list. So I would not regenerate this child. So we used the distance map as a closed list. Or you could do the same thing, but just be saying that, okay, all of this stuff is true. We have visited these before. All this stuff is false. We have not visited yet. Okay, so that's vector fields. That's basically all you need to know for assignment 2. We can take vector fields, however, and go one step beyond into something called influence maps. We are not doing influence maps for the assignment, but I just wanted to talk about them. So influence maps, typically, they're going to take a vector field, and they're going to incorporate some other logic than simple distance to a goal. And so your game may desire to have some sort of influence on the movement. And we can use influence maps for that. And I'll go into a couple of examples in a second. So influence maps can be used when it may be difficult to construct an objective function for other algorithms. So let's say you wanted to find a path somewhere. So you could use A star if you wanted to, but let's say you wanted to like avoid traps on the ground or something like that. It may actually be kind of difficult to construct a heuristic function for A star to avoid those traps. And so what you can do is you can use influence maps instead of a different heuristic function. So some examples where you may want to use this idea of influence is keeping distance from obstacles or enemies, avoiding attack damage from enemies, or any combination of a bunch of things. So let's just look at an example of how we might do that. So let's say we have a very, very simple example where we have an enemy on our grid that occupies one cell. So an influence map, now this is a very, very basic influence map, would be we would breadth first search outwards, we would find this distance map from our start to our goal, and we would simply avoid the enemy cell, right? So instead of going from this 3 to a 4 right here, we would have to go around. So we'd kind of mark this enemy as unavailable. And so we'd go around this enemy, make the path a little bit longer, but avoid that enemy completely. However, that's a pretty trivial example. Here's another type of way that we could use influence. Let's say we wanted to keep our distance from something, right? We wanted a little bit of push away from dangerous obstacles. So let's say this is a boat. Our vehicle is a boat, and this is an island. And we know that if we're too close to the island, we might crash, for example. Excuse me. So what we're going to do is we're going to use influence to keep the boat away from the island. How are we going to do that? Well, let's take the places that we don't want to be, and we're going to assign them some value. And so, for example, that value here is 10. And what that is going to mean is we are going to add a value of 10 when we're computing our distance map. And that's essentially going to be saying, I would rather go 10 extra distance on another path than step on this tile. Okay? So if we have our path here, now computed with this extra 10 distance, if we are going, okay, from our start to our goal, we would say, okay, I'm going to go to the right, I'm going to go down, and whereas before we may have gone right, now this is a very high value. So if our only option is to go there, then we would be able to go there. It's not a blocked cell. We just want to influence our agent from moving away from that cell. Okay, so you can see how this works. So we just have extra values here so that when we go toward the lowest cell, we are being guided away from these values. The cool thing about influence maps is that we can actually combine them. So let's say we had this enemy here that was like a turret, right? Or a bunker that could shoot at us. And we really don't want to be near that thing. So we assign it like a value of 50, right? If our only way to try and get to the goal was through this enemy's line of fire, of course we would have to do it, but we really don't want to do it. So if we add this influence into our map, then we will see that, okay, we no longer want to go down because we will end up in this really, really bad area. So this influence guides us away from that area. Now, in practice, we run into some issues with this where we can't just simply do it like this, but this is a good illustration of how influence can be done. And if we look at a value from this YouTube video down here, or sorry, not a value, an example of influence maps, we have two different influence maps here. One is an attractive force that red wants to follow blue, but we have a repelling force where blue wants to stay away from red. So we have a positive influence where red is trying to get toward blue, and we have this negative influence here in red where blue is trying to stay away from red. Here we have another example of that where, again, I can't remember. Yeah, so we have attackers and defenders. Defenders are drawn to attackers once attackers get into the influence area of this like home base here. So if the attacker gets into the influence map of the home base because they are attracted to that home base, then the defenders are now attracted to the attackers and they will go after them. So we can have a bunch of different behaviors, complex behaviors come out of these influence maps. But we're not going to go too deep into those because we're not implementing them for the assignment. So in the next class, we're going to be doing assignment 2. However, recall that the next class is right now. So what you can do if you have time right now is hop right over, go to the spreadsheet and look at this video. So this is the assignment 2 video, and just start from there. And assignment 2 is already up. If you follow the class download links that you were sent, assignment 2 is available. So right now you can go watch the assignment 2 video, you can download assignment 2 and do that right away. So that's it for me speaking live right now. If you want to look at assignment 2 video, you can do it right now or do it on your own time. That's fine. Just realize that it is due on March 9th. So don't wait too long for it. Great. That's it for me. This is the live portion of this class. The second half of the class is right there for you to watch whenever you want. So thank you so much. It's really great to be back to teaching. Nobody wanted to strike, but we're going to get a good deal out of it. So I'm happy that we did. All right. See everyone later. Thanks for tuning in. Bye.